As committed in our earlier session, today we have come with some crucial and important information, which is permeability of films. This session is having mathematical explanation and also have some example. We will request our YouTube students and packaging professional to understand the details, and if you have any query, then send your comment immediately so that we can help you to resolve. Understanding film permeability is crucial in packaging design, especially for food packaging industry. There are 4 types of pores in films that affect gas transmission. Number 1, microscopic pores facilitate capillary flow of gases. Number 2, submicroscopic pores create capillary channels often found in non-homogeneous materials. Number 3, intermolecular pores. These pores are relevant in the context of gas and vapor transmission through films. Number 4, intramolecular pores. Similar to intermolecular, these are also significant in films. Gas and vapor transmission occurs via Graham's law of diffusion, which describes how gases move through these pores, impacting product preservation. What is Graham's law of diffusion? Before we discuss Graham's law of diffusion, we will discuss about some topic which will be discussed in the calculation. Number 1, mole. A mole is a unit in chemistry that represents a specific number of particles, typically atoms or molecules. Here, atom means a matter is made of extremely small invisible particles or called atoms. Atoms of the same element are identical in all respects, that is size, shape, and mass. Different elements combine together to form compound atoms. Then it's called as molecules. Example, 2 hydrogen atom and 1 oxygen atom combine to become a water molecule. 1 mole is equal to approximately 6.022 multiplied by 10 to the power 23 particles, which is named as Avogadro's number. Purpose of this concept helps chemists quantify and compare amounts of substances, allowing them to relate mass to the number of particles involved in chemical reactions. Please follow the example by pausing the video to get clarity. Number 2, molar mass. Molar mass is the mass of 1 mole of a substance, usually measured in grams per mole, indicates how much 1 mole of a particular substance weighs. You can find molar mass from the periodic table, which lists the atomic mass for each element. Example, calculations: carbon dioxide, CO2, carbon, 12 gram per mole, oxygen, 16 gram per mole. Molar mass of CO2 is equals to 12, plus 32 is equals to 44 gram per mole. Graham's law describes the relationship between the rates of effusion or diffusion of 2 gases and their molar masses. It states that the rate of effusion or diffusion of a gas is inversely proportional to the square root of its molar mass. The law can be expressed mathematically as R1 divided by R2 equals to root over M2 divided by M1. R1 and R2 are the rates of effusion or diffusion of gases, 1 and 2 respectively at either side of a film, and M1 and M2 are the molar masses of gases 1 and 2 respectively at the same film. Graham's law assumes ideal gas behavior, where the gases behave ideally and are at the same temperature and pressure. Let's take an example. If you have carbon dioxide and oxygen, with molar masses of approximately 44 gram per mole and 32 gram per mole respectively, you can calculate the ratio of their effusion rates. RCO2 divided by RO2 equals to root over 32 divided by 44. The result is root 0.727, which means the final result is 0.854. This means that effusion of CO2 is about 85.4%. In other words, CO2 effuses slower than O2 due to higher molar mass. To calculate the quantity of gas diffusing through a given area of film, we can use Ficks' law of diffusion. Here we will see step-by-step guide on how to perform the calculation. Step 1. Gather necessary information. We will need the following details. Number 1, diffusion coefficient. The diffusion coefficient for the gas in the film material with the unit meter square per second. Number 2, concentration, C1 and C2, the concentration of the gas on either side of the film. The unit is mole per meter cube. Number 3, film thickness. The unit is meter. Number 4, area, A, the area of the film through which diffusion occurs. Here unit is meter square. Number 5, time, T, the time over which the diffusion is measured. Step 2, calculate the diffusion flux. Using Ficks' law, J is equals to D divided by L multiplied by C1 minus C2. Step 3, calculate the quantity of gas diffused. To find if the total quantity of gas diffuses through the area over a specific time, we can use the formula. Quantity equals to J multiplied by A multiplied by T. Now, substituting J, quantity is equals to D by L into C1 minus C2 whole multiplied by A multiplied by T. Step 4, putting it all together. Number 1, calculate J using the diffusion coefficient each thickness and concentration difference. Number 2, J into the quantity formula to find the total amount of gas diffused over the given time. Example number 1, given D is equals to 1 into 10 to the power minus 5 meter square per second. Number 2, C1 equals to 0.1 mole per meter cube. Number 3, C2 is equals to 0.01 mole per meter cube. Number 4, thickness L is equal to 0.01 meter. Number 5, area A equals to 0.5 meter square. Number 6, time T is equals to 3,600 second, means 1 hour. X, calculate J. J is equals to 1 into 10 to the power minus 5 divided by 0.01 multiplied by 0.1 minus 0.01. The result is 9 into 10 to the power minus 4 mole per meter square per second. Y, calculate the quantity of gas. Quantity is equals to 9 into 10 to the power minus 4 multiplied by 0.5 multiplied by 3,600, which is equals to 1.62 mole. This approximately 1.62 moles of gas would diffuse through the film in 1 hour. In the next session, we will discuss about another important parameters named gravity. So please do like, comment, and subscribe our channel and stay tuned.